So if the value is 1, at least one of them is 0. At least one of them is 0. And at least one of them is 0. So, and at least one of them is 0. So what is the probability? Right. Am I doing it the correct way? So yeah, well, let's try. Okay. So its value is 1. No, dfk. So the value is 1. So when the value is 1, it's either it's 1, 0, 0, 1, or 0, 0. Okay? So this happens with probability, these two things are the same, and each of them happens with probability phi 1 minus phi. So this is with probability 2 phi minus 1, and you, in that case, either, okay, and this happens with probability 1 minus phi square. Yes, it's left first, it's depth first search. So left first and then right. Okay? Oh yes, you're right. They are not the same. They are not the same. Okay. So the two, this one and this one is the only one which where we visit 2. You're right. Okay, so with probability phi times 1 minus phi, we are in this case, and we visit 2. Okay? And in that case, it's the expected cost of dfs k minus 1, given that the value is 1, plus the expected cost of dfs k minus 1, given that the value is 0. Okay? And plus 1 minus that, 1 minus phi plus phi square, times the expected cost of the fs k minus 1, given that the value is equal to 0. Okay, this is the case, this case where the first subtree that we will evaluate evaluates to 0, and this case where the first subtree also evaluates to 0. Okay, so now what I'd like to say is that we can remove this given that. What? So basically what does this mean is that this is equal to the expected value of dfs k minus 1, given that the value is 0, plus phi times 1 minus phi, the expected cost of dfs k minus 1, given that the value is 1. Okay, because these two things sums to 1. Okay, so can I remove the given? Can I remove the? No, I cannot remove that. Huh? It's changed. It's not the same value. If I know the value, it gives the thing. So. So, how many equations do I have now? So let's call UK is the expected value of dfsk, given that value is 0, and vk is the expected value of dfsk minus 1, given that the value is 1. Okay, so we have UK and VK. So what are the equation we have? We have that UK is equal to 2VK, and oh, this is good. So I can get rid of one of them. No, to vk minus 1. Too bad. To vk minus 1, and vk is equal to uk minus 1 plus phi times 1 minus phi vk minus 1. Okay. Okay, so I guess I can solve. And what I'm looking for, the cost k that I'm looking for is equal to y minus phi uk plus phi vk. So this would be nice if this would give me directly. So let's try to see what is the value of that in terms of uk, and pray so that it works, that it cancels out. What? This is equal to 1 minus that. Either you are in that situation or you are in these two situations. And these two occurs with probability. Oh no, because it's given that the value is 1. Wow. So I have to divide it by phi. Okay, I have to divide it by phi. Okay, it's given that. So it's the probability. Given that the value is 1, this happens with probability phi. Okay, so if I look at the sum here, so so what is the probability here? It will end as an exercise because I don't want to spend the whole night on that. So basically, what do we want? I want the probability of 1, 0 given that the value is 1. So we know that the value is 1 with probability phi. Am I able to read that? You know what? I will do it at home and send it to you because that's getting too ugly for me. What time is it? 18h30. Oh là là, ouais, it's way too much. I spent way too much time on it. Well, but is it true that I just need to divide it by phi? I doubt in everything now. That's, in the book, they did it wrong. I'm sure they did it wrong because they were getting an upper bound, not the exact analysis. Or maybe I...
So we can do it much quicker.
Oh, okay, that's good. Yeah, give me an easy situation. I would love it.
For example, for DFS, at first we will have to, no matter how we have to evaluate the left tree, which gives us an expected cost DFS k minus 1.
Yes.
And then with probability phi, we have 0 on this node.
Excellent. That's exactly what I wanted to say. Okay, good. So as you see, so that's the problem with probability. Okay, probability is a very, very powerful tool to get easy proof on things that are by nature combinatorial. I mean, probability is just counting. Okay, you want to count the size of some event. Okay, you have a whole probability space and you want to count the size of it. Okay. The probability is able to give you much shorter proof to things that are by essence difficult, okay? But the problem is to find this short path, okay? And this is definitely the good strategy. And I was going the wrong path, okay? I was doing good things that were probably, I think, probably correct, okay? But it was a very long path, okay? So that's the whole problem with probability. Proof got very short, but you have to find them, okay? So that's a good issue. Okay, so you're completely right. That's a good way to analyze the depth first search algorithm. The good way is the following. Thank you. The good way is the following. 1, you evaluate a tree of size k minus 1. Okay? This costs you expected value of DFS k minus 1. 2, the value is 1 with probability phi and 0 with probability 1 minus phi by construction. By construction, this is how we computed our distribution. 3 with probability 1 minus phi, it's 0, so done. Value is 1. We don't need to do anything more. Yeah, thank you very much. With probability phi, the value is 1, and we need to evaluate the over subtree. So the cost plus equal expected cost of DFS k minus 1. Yeah, this is good. Okay, this is the way it should be. So what is the cost of the algorithm now? The cost of the algorithm, the cost of DFS of k verifies the following equation. It's simply 1 minus phi, the expected cost of DFS k minus 1, plus phi times 2, the cost of DFS k minus 1. Okay? So it's simply 1 plus phi expected cost of DFA k minus 1. Okay? So simply it's 1 plus phi to the k. So remember that phi is square root of k as 5 over minus 1 over 2, which is 0.618. Okay, so what do we get? We get 1.618 to the k. Which is again the golden ratio, and which gives us a lower bound. So remember that this k is half of our k before. So basically the lower bound in terms of n. So now we have a tree of def. So now what do we have? So for our tree, our and or n tree, as def 2k. So the cost is at least 1618 to the 2k for any deterministic algorithm over distribution Q phi. Okay, this implies that the best cost of a randomized algorithm is at least 1 plus phi square to the k, to the 2k, let's say, which is equal to 4 times 1 plus phi over 4. No, this is not the right way to do it, which is equal to exponential of 2k times log 1 plus phi, which is equal to exponential of 2k times log 4 times log 1 plus phi over log 4. Which is equal to n to the log 1 plus phi over log 4. And this is about 0.969, hopefully, I think. More or less. Okay, so remember that before here we had log 3. We had our algorithm, our proof. No, phi is 1 plus phi is 1 plus 1.618.
Okay, so this one is 2 plus phi. It is 2 plus phi, not
2 plus phi? No. No, that's no, this is it.
So that's the new phi?
No, that's the old phi. That's the old phi. From the beginning, phi is 0.6. So 1 plus phi is 1.68.
But
6.8.
logarithm of phi is then negative?
1 plus phi. Logarithm of 1 plus phi is positive.
It's 4. It's
It's a 4. Yes, it's a 4 here. It's not a phi. Okay. So we had 3 here, and we have a lower bound, which is log of 1 plus phi. Okay? And it turns out that because it's a log, it's very close. Okay. I doubt it, but maybe. No, I think. Oh, okay. So for the evaluation of this tree, you can imagine that you can put over gates here. And for the non-tree, we know exactly what is the value, what is the maximum, the best we can do. Okay. So maybe it's not log 3 over log 4, maybe it's something else. Okay. But it's anyway, it's this algorithm that does the best. This is totally open for any other gates. I mean, besides trivial gates such as AND and OR. For instance, if you put the majority here, okay, and you have three inputs, and you take always the majority. Okay, finding the best algorithm is completely unknown. We have good randomized algorithm, we have some good lower bound, but they don't match. Okay, and the case is that it gets really dirty. I mean, improving, it's always possible to improve a little bit the randomized algorithm by looking a little bit forward, and it gets really messy. Okay, so that's this question is really open. I mean, you have a lot of cases where it's open, but for the non-gate, I know it's closed. I think it's closed for balanced trees. Okay. So what we've seen some good randomized algorithm. Okay. We have seen some simple way to design randomized algorithm, which is basically finding a way to randomly mix the data structure, okay, to use a deterministic algorithm on a randomly mixed data structure. Okay, this is one of the paradigms to construct a randomized algorithm. And we have seen Yao principle that allows you to get lower bound on any randomized algorithm by choosing one bad distribution and proving that any deterministic algorithm will not be able to do better than something. Okay? And it turns out that Yao principle is optimum in some sense, that you can always find such a distribution, such that the best deterministic algorithm will exactly be the cost of the best randomized algorithm, which what we will see next. I mean, so we will take a break now, 5-minute break. And in 5 minutes we'll see it for the energy saving of hard drives. Okay. So what I'd like to ask you is at 7:10, will tell me that in 5 minutes it's done. Okay, because else I will miss my train. So okay, so take a 5-minute break, and then when I come back, you tell me when it's 7:10. Okay. Good.